I think the squeeze theorem can be best explained by a practical example. Let us pick up three cricket players from the Ranji Trophy tournament played last year. Let they be Pujara, Saha and Chahal. Now, suppose we collect the data of how much runs they scored on a particular day. After collecting the data, we analyze the data and reach to a conclusion that on a particular day, Chahal has not scored more runs than Saha, and Saha has not scored more runs than Pujara. Or in other words, we may say that on a particular day during the last year's Ranji Trophy tournament, runs scored by Pujara is greater equal to runs scored by Saha is greater equal to runs scored by Chahal. Now suppose on the 30th of January last year, both Pujara and Chahal scored 5 runs each. So how much runs did Saha score on that very day? This is indeed a very easy problem, and the answer will be that Saha also scored 5 runs on that very day. This is because Saha hasn't scored more than Pujara, nor did Chahal score more than Saha. Their scores therefore were equal, such that it satisfied all the conditions. Squeeze theorem is used to solve certain limits and is also called the sandwich theorem or the pinch theorem. Now, if within the closed interval AB, function fx is greater or equal to function gx, which is greater or equal to function hx, and if the limit of function fx and hx at x approaching c are equal to L, where c lies within the closed interval AB, then limit of function gx at x approaching c will also be equal to L. If the graph of the three functions are drawn within the closed interval AB, it would have looked somewhat like this. The green line representing function gx is sandwiched between the red line representing function fx and the blue line representing function hx. The three lines squeeze or pinch at this point where x equal to c. The value of the three functions is the same at this very point and is equal to L. Now, by the help of squeeze theorem, we will prove the standard limit sin x by x equal to 1 when x approaches 0. For this purpose, we draw a circle of radius equal to 1 called the unit circle. Therefore, radius OD equal to 1. From the point D, draw a line DC perpendicular to OD. Join OC such that angle COD equal to x radians. Let OC meet the circle at point A. Join AD and from A draw AB perpendicular to OD. Here sin x equal to AB by OA. But OA is the radius of the unit circle and is equal to 1. Therefore AB equal to sin x. Again we may say that CD by OD is equal to tan x. Since OD equal to 1, therefore CD equal to tan x. Now from the figure it is clear that area of triangle CDO is greater equal to area of sector OAD, which is again greater equal to area of triangle ADO. Now area of triangle CDO is half base times height, which is half OD times CD. The formula of area of a sector of a circle is half radius square times the angle in radians subtended by the arc of the sector at the center of the circle. This comes to half OD squared times x. Area of the triangle ADO is half base times height, which is half OD times AB. Substituting the values of the sides from here, we get half tan x is greater equal to half x, which is greater equal to half sin x. First, we multiply the inequality by 2 and we get this. Then we divide the inequality by sin x and we get this. And the next step, we reciprocate the terms, as a result of which the inequality signs get reversed. Now, limit of cos x as x tends to 0 is 1. And this 1 over here is a constant term equal to 1, which can also be thought of as a function whose value is equal to 1 whatever be the value of x. So now we may apply the squeeze theorem and write that limit of sin x by x is equal to 1 as x approaches 0. We can also draw the graph of this function fx equal to 1 and this function gx equal to sin x by x, and the function hx equal to cos x within an interval minus pi by 2 to pi by 2. It can clearly be seen how the function gx is sandwiched between these two functions and is squeezed at a value equal to 1 at x equal to 0. Now we will evaluate the following limit by the help of Squeeze theorem. This limit is nothing but the derivative of tan x. To prove this, we again draw a unit circle whose radius OE equal to 1. From E, draw line AE perpendicular to OE. Let the angle AOE is equal to x plus delta x. Draw a circle of radius OA taking O as center. Draw a line OB cutting AE at D such that angle DOE equal to x and angle AOD equal to delta x. Draw another circle taking center at O and radius equal to OD. Now AO by OE is equal to sec x plus delta x, or AO equal to sec x plus delta x, since OE equal to 1. Similarly, OD equal to sec x. Again, AE by OE is equal to tan x plus delta x, which means AE is equal to tan x plus delta x since OE equal to 1. Similarly, DE equal to tan x. Now, area of sector AOB of the large circle is greater or equal to area of the triangle AOD, which is greater or equal to area of sector COD of this circle. Now, area of sector AOB is equal to half AO squared times delta x. Area of triangle AOD is equal to half base times height, that is half AD times OE. Here AD is the base and OE is the height of the triangle. The area of sector COD is equal to half OD squared times delta x. We now substitute the values of AO, OE, DO and AD. AD is nothing but AE minus DE. Thus we get half delta x times sec square x plus delta x is greater or equal to half tan x plus delta x minus tan x, which is greater or equal to half delta x times sec square x. Now we multiply the inequality by 2 and then divide it by delta x, and we get sec square x plus delta x is greater or equal to tan x plus delta x minus tan x by delta x, which is greater or equal to sec square x. Now limit of these two functions is equal to sec square x as delta x approaches 0. So we may apply Squeeze theorem and conclude that limit of tan x plus delta x minus tan x by delta x is equal to sec square x as delta x approaches 0. Thanks for watching this video. In my next video, I will come up with typical problems on limits where we may apply the Squeeze theorem.